through the plus and minus is just like to express 1 through plus, and then substitute it into minus, and then take out 0. Okay, anyone? Yes?
One of the square root of 2 of the plus state plus the minus state.
Yes, exactly. Does everybody see why it's the case? Yes.
Is it wrong to think about it as plugging in the 0 state into the formulas for plus and minus there?
Oh, I mean, yes. I mean, you can take this representation and plug in into here. So I don't quite understand the question.
If I think about it as saying the 0 state is 1 times the 0 state plus 0 times the 1 state. And then I kind of replace the 0 state and the 1 state by those coefficients in that formula. And then I write that down as the coefficient for the plus and the minus state. I'm not sure I'm making sense.
I'm not sure where, so you said tensor product, or, so there's no tensor product here yet. So, okay, so the way we do it is, I mean, so here it's clear that 0 is 1 over square root of 2 or plus minus, because, yeah, we can just calculate, we just can verify that this is correct, right? This is 1 over square root of 2, 1 over square root of 2, 0 plus 1, plus 1 over square root of 2, 0 minus 1, right? So what we get here is 1 over square root of 2, 2, so there's going to be, so 1 goes away, right? Here and here. And we're left with 1 over square root of 2, 0 by 2. And this is just 0. So the way to understand it is that, like, again, bras and cats are just, so the bras are just the notation for the vectors in a vector space. So there is these 2 particular vectors that I chose, which I label as 0 and 1, which is 1. And then in terms of these 2 vectors, I just define vectors plus and minus. So it's like, if you remember your linear algebra, I'm just going from one basis to the other. And here, instead of in the linear algebra, we just write the vectors as the columns. Then here, what we do is, instead of writing the columns, we just say, oh, we label this vector as 0, we label this vector as 1, we label this vector as plus, we label this vector as minus. And that's it. And basically the whole, if we look at it, the whole language of quantum mechanics is the language of the linear algebra and vectors and transforming from one basis to the other. Yes?
Why are plus and minus vectors useful?
So this is useful for the following, also for the quantum computing cases. So for example, there are certain gates in quantum computing, and which are called poly gates. So it's X, Y, and Z gates. And for example, for the Z gate, the basis of the Z gate, which can be seen as a 2x2 matrix. Its eigenbasis is 0, 1, and the eigenbasis of the X matrix is plus minus. So this is for the future reference. This is the eigenbasis of Z gate or Z operator, but we haven't gotten to the operators yet. So, and this is the eigenbasis of the X operator. So the eigenbasis means that if I act with this matrix, this operator on this vector, I get out the same vector with its eigenvalue. Does it answer the question?
Yep.
Okay, perfect. Okay, so this was hopefully getting you a bit more comfortable with this notation. So now a bit about the Bloch vectors. So the Bloch vector, as Lidia also mentioned, it can be understood as the conjugate transpose of the ket vector, which basically means that, for example, if we have, now let us take an arbitrary Hilbert space and take a state in this Hilbert space, which we label as psi, and say that the Hilbert space has the basis, which we label as I, where I goes, say, I don't know, from 1 to D. Or maybe to be more 1, so on. And there we can just decompose this vector in terms of the spaces with some coefficients, let's say AI, I. Then the bra of psi would be the conjugate transpose of this. And if we say that we label the conjugate transpose of I, just this bra I, then what we get here is sum over I, AI conjugate bra I. Okay, let us consider an example. So suppose that I have a state psi, which is, I think so, e to the power I phi 0 plus, sorry, over square root of 2 plus 1 over square root of 2, 1. What is going to be the bra vector? So remember, just use this formula, or just directly take the conjugate transpose of this vector. Yeah, anyone? Yeah, don't be shy. It's okay to be wrong. This is just the first exercise. You're getting comfortable with the language. You know, when you learn the language, you always make tons of mistakes. Yes?
E to the minus I phi.
Yeah.
Plus 1 over square root of 2 and
Yes, exactly. Does everyone see why it's the case? Yeah, okay, there are no questions. Yes.
The conjugate of the e to the power of I phi, so always the minus I phi.
Yes, yes. So just a reminder of some material from the complex analysis. So, or just like complex numbers. So the way to see e to the power I phi, so this is the complex plane, right? So this is the real, this is the imaginary. And then the complex numbers live in this plane. And then if we draw a unit circle with the center in 0, so this is a circle with the radius 1, then every point on the circle corresponds to a particular complex number, which can be parameterized by simply this angle phi here. And the way we can write this complex number is, so I don't know, let's say it's z, it's cosine phi, because here we have the cosine, plus I sine phi. And then if we take the complex conjugate of z, then we get cosine phi minus I sine phi. And this corresponds to the basically the mirror of this point with respect to the real line. So minus phi, basically. So if this is e to the power I phi, this is e to the power minus I phi. Does that answer the question? Yeah, okay. Okay, well, what's the time? Yeah. Okay, so this was how we represent psi if we have a finite dimensional. Yes.
Question on Hilbert spaces.
Yes.
So you mentioned that the Hilbert space is vector space where R goes from 1 to 0.
Yes, for example.
So there can't be like any non-natural number just 1.5.
No. No, so we consider either finite dimensional vector Hilbert spaces, vector spaces where we have which can be described by finite dimensional basis, or infinite dimensional Hilbert spaces where the basis is continuous, so to say. Yes, it would be uncountable. Like, for example, now we will consider the position basis, which is, and the position is, so position is a continuous variable, and then the sum, for example, there turns into an integral.
Also, the Hilbert space has a kind of length 1.
Sorry, length 1.
Yeah, the normalization.
So there is no normalization constraint on the Hilbert spaces itself. There is a normalization constraint on the states of the quantum system. So basically, the state of the quantum system has to be normalized. So yeah, this is something I didn't mention. Basically, what this means is that, for example, like here, if we take this this state psi, then we see that the psi, which is just the bra psi by ket psi, which corresponds to the inner product of psi of the vector psi with itself, it has to be 1. So this is the this is the constraint we impose on the vectors that can describe the state of a physical system. And this is connected to the fact that in the end, what we want to describe, like, for example, in a continuous case, when you take a wave function, the modular square of the wave function corresponds to the probability. And then the probability has to sum up to 1, basically.
So states of quantum systems are subsets
subspace, Euler subspace at Hilbert space.
Subspace with a Hilbert space, yes.
And the wave function for discrete Hilbert space is going to just imagine a vector.
Sorry, the wave function? I didn't hear.
Try to find some alternative wave function for the discrete Hilbert spaces. Then it would just map number to number and have like the entries for three-dimensional Hilbert space.
So if there is a map which maps one Hilbert space to the other, it would just map one vector to the other. That's what you mean?
If we use this sum notation that we did for a three-dimensional Hilbert space,
Yes.
we could try to find a discrete wave function. This discrete wave function would be just mapping into its dimensions.
Yes, I guess I'm not completely understanding your question, to be honest.
Discrete mapping function for the discrete Hilbert space.
I mean, this is the wave function basically.
Yeah, so it's just taking some vector with entries.
Yes, exactly. So this is just taking a finite dimensional vector and yeah, with some entries. Okay, so now let us go to the continuous case. So, okay. Maybe one more comment just to make things clearer. So when we talk about the ket psi, this is an object that lives in a Hilbert space. When we talk about, for example, the coefficients AI, which describe it in a given basis I, this is just a representation of this ket psi in the given basis. Like as you have seen here, when we go from one basis to the other, these coefficients change. They can change because, for example, in 0, 1 basis, the coefficients are 1 over square root of 2, 1 over square root of 2. In a plus minus basis, the coefficients are 1, 0. And this is crucial because then we see that psi is just an object that lives in a Hilbert space, but the way we describe it depends on the representation that we choose or the basis that we choose. And then we kind of decompose our state in a particular basis. So the way we go is, so we have this kind of discrete representation, and from this we kind of go to the continuous case of the infinite dimensional Hilbert space by just writing that psi is an integral of psi over of x dx, where x is the so-called position basis. So this is just one basis that we can choose. For example, another basis that we can choose is so-called momentum basis, but we will see this a bit later. So to give you an example and also introduce one more concept that we will need. Yes. Is it better?
Yeah, it's pretty good.
Okay. So let us consider a following physical situation. So when I say position basis, this is actually corresponding to the position. Yes.
Question. Script that you provided, they used a different notation than this and that. They didn't use the get around the psi. It just said psi itself is an integral, not the head of the psi.
Yes, or
The psi gets psi gets.
Yeah.
It's strictly didn't have the get around the psi.
This is clearly this is probably a typo.
So it should be a get is an integral.
Can I quickly see the? Yes, this should be a cat. Sorry, thanks for pointing this out. We'll change it. I mean, it has to be a cat because you have a cat here, and you can still think about these cats as vectors, but they're kind of a continuous limit of this finite dimensional vectors up here. Okay, so let us imagine the following physical situation, which is going to be slightly idealistic, but this is the examples we usually consider. So suppose that there is a particle which is known to be exactly at the position x0. And then we want to describe the state of this particle. So the corresponding ket, which we label the state of this particle, is just x0, because we know it to be exactly at the point x0. Now the question is, what is its wave function? So the wave function in this case is the representation of this state in the position basis. So we need to see what psi of x is, which is just a function. So to describe this, we use so-called Dirac delta function. So it's delta of x minus x0 x dx. It's integral from minus infinity to plus infinity, which we usually take. So what is the idea of the Dirac delta function? By the way, is everyone comfortable with the Dirac delta function or not so much? Okay, let me then quickly recap it. So, by the way, now the things that I'll be saying, this is how we understand and use Dirac delta function in physics. If you talk to a pure mathematician, simply seeing this integral will make them mad. Because if you go into mathematics, this is not a function, this is a functional, which acts on a space of functions, and then so on. So for example, my mathematical, function analysis lecturer in my bachelor's, he said that if I ever see you write delta function integral, you'll get no pass at the exam. Yeah, completely thrown out of the course. I don't want to talk to you. But as a matter of fact, his wife was a theoretical physics professor, and I took seminars with her, and she would write the delta function in each integral. So I guess it's not as bad as he says. Anyway, and we'll understand it as more of a physical object. So suppose that you have the function f of x, and which is defined. So for all x in R, and is also finite everywhere. And then suppose that you want to find some way which would allow you to filter out the value of this function at some point x0. So how do we approach this problem? So sometimes as we've seen, it is useful to start with the discrete case. And in the discrete case, for example, if we have a sequence, let's say A1, A2, so on. Basically, it can be a countable sequence or uncountable sequence. Sorry, probably, sorry, what I wanted to say is can be finite sequence or a countable sequence. How do I select a particular AI from this sequence? So what I do is I can just write AI as sum over all j, then delta ij, aj, where delta ij is the following beast. So delta ij is 1 if and only if I equals j, and 0 in all the cases. So basically, if I write out AI as the sum with this delta ij, the only member of this sum which will be non-zero is AI itself. So I can clearly, so this is clearly justified. And this is called Kronecker delta. This is also used, for example, if you have a discrete basis, and then you want to write that the members of this basis are orthogonal, which means that all inner products except for the inner product of the vector with itself are 0, which means that ij is delta ij. Okay, and now we go to the continuous case. Where we just say, okay, now here we have the sum, and now we can substitute it by an integral over x. And instead of the sequence, we just have the function. And we want to know the value of the function at the point x0. Then let me start by writing out the right-hand side of this. So this is from -infinity to +infinity. Dx delta of x minus x0. So this is the same as this delta Kronecker delta, but for continuous case, when we want to select out x0, f of x. And that singles out the value of the function at the point x0. Okay, so this is a bit of an artificial structure. How can it be seen physically? What's the time? Okay, let me finish with this physical demonstration of the delta function, and then we can have a short break. Is that good? Yes. Okay. I mean, this is just the convention. I mean, the convention. You can write dx, yeah, anywhere. So I mean, usually people write dx near the sign of the integral because it makes clear what is the integral taken over. I mean, okay. So the convention here is that if you don't see me putting any brackets, like any things like this, then by convention, let's say that I'm integrating over everything that's on the right of the x. Yeah, yeah. So this is just a convention. This might be like useful later when if we want to integrate over more than one variable. then it makes clear like to which variable each integral is taken over. So, and also if you have like different so if you take, for example, integral over x from a to b and integral over y from c to d, it's good to indicate where is the integral over x and where is the integral over y. So this is basically with this. But you can also write it at the end if it's clear what you're taking it over. Okay, so how can we see kind of this delta function physically? So suppose that we have some function, which is f of x. And then what we start with is we just take some infinitesimal window here around the point x0 minus epsilon to x0 plus epsilon. And then, for example, if we take, let's say g of, if we take the following, so if we take integral f of x from x0 minus epsilon to x0 plus epsilon, add 1 over 2 epsilon and dx, we integrate it over dx, then what we get is 1 over 2 epsilon goes out. And here, let us call the integrand of f of x as a big F. So f of x is such that f prime of x equals small f of x. Then here what we get is big F of x0 plus epsilon minus big F of x0 minus epsilon. And if we take the limit of this expression as epsilon goes to 0, then what we get is, we have here the limit. What we get on the right-hand side is exactly the definition of the derivative of the big F at the point x0, which is just the function small f x0. Which means that if we take the function which we will now call the delta, which will be 1 over 2 epsilon, sorry, just the limits when epsilon goes to 0, 1 over 2 epsilon as the x lies between x0 minus epsilon and x0 plus epsilon, and 0 everywhere else. So basically, it's going to be like a very, since we're taking epsilon to 0, in the limit, it's going to be like a very, very thin rectangular function centered around x0. And if we take the limit of this function, then basically we would just and apply it to the f of x and take the integral over dx as we did here, then what we get is the value of f at the point x0. So you can see kind of this delta function as this the limit of this very small rectangular-like function, which is centered around the point x0. So this actually cannot be taken as definition, like as a strict mathematical definition. But this, I hope, allows you to get a bit more kind of feeling of what is the limit of what the delta function is. Yes?
So why do we write x minus x0, not just x comma x0? Isn't this just a function of not a two-dimensional function in a sense. We can use both x and x0.
I mean, usually when we write it in the function, so this is, delta function can be seen as a function of two variables, which are in there, which in this case are x and x0. But usually we only integrate over one of them. So, but yes, it can be a function of two variables.
So this is now say like say delta and subscript x0. So that's just like one variable and set it x0. Where does that have to do? Like instead of splitting it as an x0 as input, you just say delta function has x0.
I mean, the way we write it is just a convention. So we can also write it. So this is just the mathematical convention that we write it delta of x minus x0. We can also write it as delta x x0. So I mean, the meaning is that it's just like this filter which points out the value of the function f at x0.
And sometimes you use this delta function in discrete case as well. Does that just mean that
so when we use it in a discrete case, it corresponds to the Kronecker delta, basically.
So it's the same, take one, it's not zero.
Yes, exactly. That's the idea. Okay, let's make a short break and restart in what is the usual break now? 10 minutes or 15 minutes?
As far as I know, it's 10 and then it's up to 5 to 12, is correct?
Okay, then let's make a break of 10 minutes and restart in 20 post 11. Okay, sorry that the break was going a bit over. There are lots of good questions. Okay, so I hope now it's more or less clear with the delta function. Please like take time to absorb this. You don't. It's not required that you understand it right away. Give it some time. There's the thing. Okay, so now let's talk a bit about exercise sheet. Do you see the brush? Yes. So in the exercise sheet that is posted on Moodle, there are 3 exercises. So the only exercises that you need to solve are 1 and 3. So we'll update the sheet today and remove the exercise 2 because it's a bit more advanced, and we'll keep it for the one of the next exercise sheets. So in the exercise 1, this is something that we already talked about. You'll just like look at the vectors and states of the 3-dimensional Hilbert space, and just play around with bras and cats and normalization. So this 3rd exercise is a bit more interesting. It's about the Bloch sphere, which Lidia, I believe, mentioned in the lecture. And Bloch sphere is very important for understanding how we can graphically represent the states of a qubit. So just to remind you, qubit is a 2-dimensional quantum system. Which is so we have the Hilbert space corresponding to 2-dimensional system, and the usual basis that we choose to describe the states in this space is the 0-1 basis, which is also called the computational basis. Okay, so and then we just say that any state of the qubit can be described as the linear superposition of the states 0 and 1 with some coefficients alpha and beta, which are complex. Okay, and it also has to be normalized, which means that alpha squared plus beta squared equals 1. This follows from the fact that psi bracket has to be equal to 1. So now the question is there a nice way that we can represent any state of the qubit given this coefficients alpha and beta? So what I claim is that for any state psi which belongs to this 2-dimensional Hilbert space, we can write it out as cosine theta over 2, 0, plus sine e to the power phi sine theta over 2, 1. So instead of just writing these two coefficients alpha and beta, which are connected by this normalization condition, now we just substitute them with another two parameters, theta and phi, where theta is from 0 to pi, and phi is from 0 to 2 pi. And given that we have these two angles, theta and phi, this indicates that we can find a correspondence of the state to some point on on three-dimensional sphere. So these are just can be seen as polar coordinates. So we have this 3 dimension, and then we have a sphere around the origin of radius 1, and then each point on the sphere corresponds to the state psi. And we will see to which state correspond to which points on the sphere. So yeah, now let us first prove this statement. So, is there a question? Yes.
So for the range of theta phi, we actually
Oh, sorry, I didn't hear.
we actually include pi or 2 pi respectively for the range of theta phi.
I mean, okay, so the question was whether we include pi and 2 pi into the range. So, I mean, for phi, we don't have to include 0 and 2 pi because it's up to 2 pi anyway. And for theta, so for theta, we need it. Yes, so here, I guess the correct way would be this.
I think that's why like this. Why do you need pi? Why do you need pi in one for not 2 pi in the other?
For theta and phi.
Yeah.
So phi is the angle in this direction, and theta is in this plane. So if you remember that, so say x, y, z. So in 3D, there are different systems that you can choose to describe the points, right? So you can choose x, y, z, and then you can also choose polar coordinates, which are r, theta, and phi. And these are exactly the polar coordinates, but all points we're considering have r equal 1. So they're on a sphere of the radius 1. And then the phi corresponds to this angle in an xy plane, and theta corresponds to the angle with respect to the z-axis. So, and I believe that for polar coordinates, these are the same, the same range. Okay, so let us start with psi in our usual form that we had it before. Then let us rewrite alpha as modulus alpha, and its phase, which we call the arc alpha 0, plus we do the same for beta. Modulus beta e to the power I arc beta 1. Here, what should I do?
I mean, any state is this up to global pricing?
Ah, yeah, okay. E to the power I don't know, so phi global. Yeah, so this is up to global phase. Oh, yeah, thanks. Yeah, this is actually comes in right here. So is it clear that for every complex number we can write it as the modulus of a complex number by the phase? Yes. It's not clear. Okay. Let us come back to the complex numbers. So again, we have our complex plane, real part, imaginary part. Then each complex number is a point in this plane. So let's say this is Z, this is A, this is B. Okay, so Z is A plus BI. How can we represent Z? We can also draw this. We can also see Z represented in polar coordinates in 2D plane, which means that what we need is the distance from Z to the origin, which happens to be square root of A modulus plus squared plus B modulus squared, which is basically the modulus of Z, and the angle phi. And this again can be also seen as if we're looking at the circle with the radius modulus Z, and then Z is the point which is characterized by this angle phi here. Arc alpha is the phi here. It's this angle phi. So Z can be written as Z by e to the power I phi. So if you convince yourself that for every point on the unit circle, it can be written as e to the power I phi, what we do, we just rescale the circle so that the radius is modulus Z. And then we can write Z as modulus Z, which is the scaling factor basically by the angle, by this e to the power I phi, which corresponds to this, to just taking this angle phi from the real axis anticlockwise. Yes, so for example here, arc Z is phi. Yeah. Okay. Is this clear? Yes.
As an engineer, how do you want to describe we use J for the imaginary unit instead of phi in the relation?
Okay, one comment for everyone. Can you speak a bit louder because there's also the screen which.
So if we can use the letter J for the imaginary unit instead of phi.
Yeah.
J sometimes used for indices, JKL, but if you use J,
Yeah. It's usually clear if you mean an index or you mean an imaginary I. So yeah, feel free. Okay. Given this, what we can do here now is we take out a global phase, which is, let's say, e to the power I arc alpha 0 plus e to the power I arg beta minus arg alpha modulus beta 1. Then this, since we're only considering this quantum system in this two-dimensional Hilbert space, we're not considering any interactions with anything, then we can discard this global phase and then denote by phi arg beta minus arg alpha. So this is just note, this is global phase. And we discard it. Okay, what we arrive to is the following then. Alpha 0 plus beta e to the power I phi 1. Okay, then we have the next step. We know that the U2 normalization condition modulus alpha squared plus modulus beta squared is equal to 1. And for any alpha and beta modulus alpha, modulus beta, which adhere to this relation, we can write them as just a cosine and sine of some angle. So cosine theta over 2 and beta is sine theta over 2. And I mean, this is true because sine squared plus cosine squared is always 1. And from this, that follows that we can write psi as cosine theta over 2, 0, plus e to the power I phi sine theta over 2, 1. Okay, is this procedure clear? Yes.
Where does the global phase come from? So we start the global phase on the left. Where does it come from? So I'm confused with the words. Because at the beginning, when you wrote that down, the global phase was not there, and it's only there. Why is it global phase part alpha, not something different?
Okay, so here again, the global phase, if we're considering this one isolated system, this is something that we can always add or take away without any consequences for us, without any, let's say, consequences that we can measure. Here we want to get to this representation, and here we see that in this representation, if we take out this, let's say, global phase, the coefficient in front of 0 is real. Yes, it's real. So here, when we transform this equation, we want the coefficient in front of 0 to be real. So hence, we just take out e to the power I of argument alpha.
Called global phase that e to the power I phi is in front of state.
Yes, this can be so that phi global, if we retain to that notation, phi global is just the argument alpha. Does this make sense? Okay. Okay, I need to finish soon. So now let us just, as a last thing that we'll consider today, let us see where we can find different states on the Bloch sphere if we have this. representation. So essentially what we're going to do, we're going to take some states we already seen, like for example, 0 state, 1 state, a plus or minus, and then determine the parameters theta and phi for these states. So while I'm erasing the board, what you can do already, just take state psi, a state 0, and try to calculate parameters theta and phi. Okay. Let's see. So I need to represent it as cosine theta over 2, 0 plus phi sine theta over 2, 1. Okay, so what is theta here? So you just need to find coefficients theta and phi such that this equality would hold. Yes?
0.
Yes, exactly. And phi? Yes. Yeah, it can be anything. What about if it's 1? So this is supposed for 0. Then if we have here not 0, but 1. So for 1, theta is, yes, yes, exactly. And phi? Yes. 0, that's correct, but in fact it can be anything because this is anyway up to global phase. And when theta is phi, then this disappears basically, and then you have e to the power I phi sine theta over 2, 1. So basically, and then sine theta over 2 is 1, so you just have e to the power I phi 1. But then since it's up to the global phase anyway, then phi can be anything in this case as well. Okay, a bit more complicated case, which is not as complicated, but anyway. So we have plus, which is 1 over square root of 2, 0, plus 1 over square root of 2, 1. And we still want to write it as cosine theta over 2 plus e to the power I phi sine theta over 2, 0 here, 1 here. So what is theta for this case? Yes. Yes, exactly. And phi? Yes.
0.
Yes, exactly. And now the last example for today, we'll consider minus state. So the minus state is have minus, and here we have minus. So what is theta in this case? Yes. Yes. But phi? Yes. Is it clear why this happens? So here we have to, make use of the facts that e to the power I pi is -1. So the easy way to see it is, again, imagine e to the power I phi as this points on the unit circle, and then e to the power I pi corresponds if we choose a point which is rotated by pi anti-clockwise from this point on real axis. So it goes here, it goes to the opposite side of the real axis, so it's -1. Okay, so now for the plus and minus, for example, one can draw them on the sphere. As the following points. So plus is going to be here because it's rotated by pi over 2 in this direction, but phi is 0, so it's still on the x-axis. And then minus will be on the other side, basically, because minus will be rotated by pi over 2 as well, but then so if we rotate it by pi over 2, but then we need to also rotate it in the xy axis by pi, so all the way to the other side. Okay, and in the exercise there are going to be some other states, and of course I forgot. The 0 and 1 states are this state and this state, because so the 0 state theta is 0, so it's not rotated, so it's going to be just on the z-axis, and 1 and the state 1 is rotated with respect to this point by pi, so it's going to be all the way down here. And in the exercise sheet, there's going to be 2 more states that you'll have to draw on the sphere. Also, in this exercise, something that I didn't have time to cover, you'll see some gates. So gates are operations that we can apply to a qubit, and they map one state of the qubit to another state of the qubit. And another reason why this Bloch sphere is useful is that some operations which we can apply to physical qubits can be seen as rotations on the sphere. We just map one point on the sphere to the other by rotating it with respect to z-axis, x-axis, or y-axis. And then in the exercise, you'll see the examples of how these gates look like. Yes.
We have seen bases like plus and minus, which are basically on the x-axis, and the basis, the computational basis is 0 and 1, which is on the z-axis.
Yes.
Is there also corresponding basis on the y-axis?
Yes, there is. You'll see it in the exercise sheet. I mean, in fact, like if you take any point on the sphere and then take the opposite point on the sphere, they will form a basis.
What is the y-basis basis, which is on the y-axis also used commonly in practice, or is it more general?
Yes, yes, it is.
Can you explain why the pi can be anything in stage 1?
Okay, so this is what you see when you directly plug in the theta. So here it's clear that theta is pi, right? So if you plug in pi and you want to determine phi, so if you plug in phi here, then you get what you get is here you get 0, and here you get e to the power I phi 1. But e to the power I phi 1 is in any case equivalent to the 1 state, because phi is, we can discard phi as a global phase. So whenever you have a state psi and a state e to the power I phi psi, if you're talking about only this isolated system, then you can always like say, I don't care about phi, these two states are equivalent. Okay, I think that's it for today. Thanks a lot for coming here and also asking questions. This was very helpful. Please continue to ask questions in the future. So now we're finished, and I think the lecture starts soon. But if you have any remaining questions, just come up to me and we'll try to sort it out.